We're coming up to class J here, spinors. Spinors are really cool objects, very important in physics to understand the spin of the electron. But our focus in this class is going to be on mathematics rather than physics. To set the foundation, we're going to integrate the concept of the group to matrices and conditions on matrices and find that there's a richness in group theory as applied to matrices. And then we'll also talk about what an eigenvalue is and an eigenvector. And all this will be used later in the course as we apply it to the electron. But what I'm particularly proud of in this class is to answer the question as to where the Pauli matrices come from. When I was a student, I remember seeing the Pauli matrices pretty much, given to me on a silver platter. And I have a way to show you a natural way to see how the Pauli matrices can come out of our analysis. And I hope you enjoy that, and it will give you great insight into the Pauli matrices. And when we apply them to the electron, it'll be building on the foundation that we do today. Chapter J, spinors. J1, fun with matrices. Now we're going to look at the spinor and matrices. These are going to be a discrete kind of way of looking at things. This will help us understand the spin of the electron eventually. So rather than have a continuous kind of a situation, we're going to have matrices here where you can have like a state B and spin up or spin down, for example, but that will be explained later. So first off, let's give a 2x2 matrix A, which has 4 components. And sometimes here they'll label this one first row, first column, first row, second column, second row, first column, second row, second column. And we'll use this, and sometimes we'll use the other. 1, the trace. The trace of a matrix, TRA, is to add the diagonal components, A plus D. 2, the transpose. Now for the transpose, we put a little T for transpose as a superscript, and that means to take the off diagonals and flip them, so swap them. So this is AC and this is BD. If you had this general case, you could write it as an AIJ, where I is the row and J is the column. And for the trace, what you would basically do here is switch to J in the I. So if it's diagonal 1, 1, switch 1, 1, still 1, 1. So you don't do anything with that. So for the 2x2, you're just switching these two. Now notice that the trace of a transpose is the trace of A, the same, the matrix before transposing, because A plus D in either case. 3, the complex conjugate. For the complex conjugate, and we'll use a star here in physics. In math classes, pure math, a bar over the A's, you might encounter it there. But here we're going to use the physics terms. This would be the complex conjugate of each entry. And remember, if you have z is some real value plus some imaginary component times y, where y is real, then when you take the complex conjugate, you just go in there wherever there's an I, you make it a minus I. So the matrices can have complex numbers in there. The next is the Hermitian conjugate. Now for the Hermitian conjugate in physics, we use the dagger. Now in math classes, you might see a star or something. And I had a math professor once told me that notation really doesn't matter because at the cover of each math book, he says they define their notation and you just go with whatever that book says is the notation for that book. So this is the notation for our class, what we're doing here. So the dagger, what you do is you're going to swap, you're going to do a transpose, you're going to swap the B and the C. Because so you have A, B, C, D. We're going to swap the B and the C. We're going to do a transpose. And then we're going to do the complex conjugate. So then we'll star it. So what we're doing here is we're taking the transpose and then we're starring it. But you could have taken the star first and then swapped the C star and B star. So you could also write this as A star and then do the transpose. 5, the determinant. For the determinant, we can write DETA. And sometimes, by definition, they just go ahead and put a vertical line on either side of the matrix. What you do is you take A times D minus C times B. So I'll just write the matrix again here. A, B, C, D. So you take A times D, and then you subtract C times B. Or if you want to write the B first, you could. 6, the inverse. The inverse. Now, the inverse matrix, I'll put a -1 superscript, is such that if you take A and multiply it by the inverse, you get the identity. And the identity is 1, 0, 0, 1. Of course, if you multiply a matrix by this identity, you get the same matrix. But we have to have a caution because some matrices don't have inverses. Like, for example, this one here will have no inverse. Now let me show you why. If you take, say, B, and you're looking for another matrix, A, to be a candidate for, say, the inverse for B, you would have 1, 0, 0, 0 times the A, B, C, D. And remember how you multiply matrices, you're going to take 1 times A plus 0 times C. You take this, turn sideways, smack it against there sideways. And that gets you this first one. So 1 times A plus 0 times C is A. Then you take these two, turn sideways with this. That's 1 times B plus 0 times D. And then here, you take the 2 zeros, turn them sideways, get 0. You smack these sideways against there, you get 0. See, there's no way you're never going to be able to get, you can't get this because there's a 0 there and you need to have a 1 there. So that's an example of a matrix that does not have an inverse. Let's look at a couple cases. And let's say we have the matrix 3, 0, 0, 4. And we want to find an inverse for that. So we'll put A, B, C, D. And we're going to then take, we want A, the A inverse, we want that to be equal to the identity element. So if we have 3, 0, 0, 4 times A, B, C, D, okay, we turn this sideways, so 3 goes with the A, 0 goes with the C, you add them together, you get 3A. 3B is up here, plus 0D. 0A plus 4C would be down in here. And 0B and 4D would be down in there. So what we want here is we want this thing to be the identity matrix. So in other words, we want 3A to be 1. We want 3B to be 0. We want 4C to be 0. And we want 4D to be 1. Now that means that here we can write down what the A inverse is. A has to be a third, and the B is going to be 0. C is going to be 0, and D is going to be 1/4. Let's check that out, see if that works. All right. We could take here A with A inverse. It's 3, 0. I mean, it really should work because, we solved it, but it's not bad to check. So 3 times a third is 1. 0 times 0. And you turn this sideways there, you get 0. You turn that sideways there, you get 0. And if you turn that sideways there, you get the 1. So it works out. So 3 times a third plus 0 times 0, that's going to be 1. 3 times 0 is 0, plus 0 times a fourth is 0. 0 times a third is 0, plus 4 times it is 0. And 0 times 0 and 4 times a fourth is 1. Notice that this can be written as, if we want, watch this trick, we put the common denominator, say 1/12 out there, and then we could have a 4, 0, 0, 3. And that's kind of cool to write it like that because you see the determinant of A is 12 minus 0 is 12. So this is actually saying 1 over the determinant. And that's insightful. It's relevant. So let's come up with a rule here. Rule 1. What we did here is, if we compare these two, we swap the diagonal components and we divide by the determinant. So that's rule 1. Swap diagonal components and divide by determinant. Okay? And this will work with imaginary numbers too, and complex numbers in general. Okay, so now what we're going to do is we're going to try another one. Let's try, when we have the 3, we had a 3 here, and we had a 4 there, and we had a 0. Let's put a 0 here, but let's put a 1 there. Let's look at that one. and multiply by some, say, general matrix like this, and see if we can get a solution to find an inverse. Well, if you take 3 times A plus 1 times C, that has to equal the 1. That's this one up here. If you take 3 times B and you add 1 times D, that has to be equal to 0. Because you turn this sideways on here to get that upper one, so 3B plus D. Now, if you take the 0, 4 this way, it will get you that 0. So 0A that's a 0, so you get 4C will equal that 0. And the last one, 0 times B plus 4 times D, that's going to equal 1. So immediately you can see here that the C is going to be 0 from here. The D from here is going to be 1/4. But see, if the C is 0, that means the A has to be 1/3. Now we just have to find B. Well, to find the B from this one, this says 3B is minus D. B is minus D over 3. So that means you're going to be talking here B minus 1/3 of a 4th. Of course, the 4th is the D, so that's minus 1/12. So that means what we're finding here for the inverse, A, B, C, D, right? For this case, we have 1/3, a minus 1/12 by just finding the numbers and plugging them in, and then the C is 0, and the D is 1/4. And we can write this out by pulling out that common denominator again. Here, 12, 1/12 is going to be pulled out. Then we have a 4, a minus 1, a 0, and a 3. So this is 1 over the determinant, and then 4 minus 1, 0, and 3. Now we're going to come up with the rule 2. Notice that rule 1 still applied. Rule 1 was to swap the diagonal components, so 3 and 4th got swapped. And we also divide by the determinant, and that was the rule 1. Rule 2 is going to be here to put a minus sign in front of off-diagonal components. Now, I'm not proving that, but if I had one down there, actually it would have the minus 1 down there. So I'm going to just go ahead and state this rule without a rigorous total proof and say that you put minus signs in front of off diagonal components. Okay? Now, if you were taking a math course in matrices, you'd be more rigorously looking at all this stuff and finding the inverse of a 2x2 in general, some general formula. And here I'm taking a more of a, say, a physics approach to like come up with some observations. All right? So now let's go on to J2. And these are the unitary groups. Now, matrices will form groups. You can form groups. You could, for example, take matrices, and they all have to have inverses now when you do this. But if you take n by n matrices, and then you have the binary operation of matrix multiplication. The definition of unitary is that if you take the Hermitian conjugate of the matrix, the dagger, that's equal to the inverse. Let's look at U1, where that 1 refers to n. So this is like a 1 by 1 matrix. So if it's a 1 by 1 matrix, that means the matrix will just have one component, which I'll call little u. Now the U dagger means, remember, that we need to do a transpose. Well, if you transpose this, you get the U back. There's nothing really to, I mean, this is just like A11. Well, A11, switch the ones, you get A11. So this would be U, and then you have to star it, because that's what the dagger does. It swaps the off diagonals and gets you a star. And that means here, for the this case to be true, the U dagger has to be given U the inverse, so this has to be 1. So that means if we do this matrix times this matrix, that would be the matrix U star. And this inside here has to be a 1. So identity, because this has to be the inverse. If this is the inverse, then you're going to get the identity, and the identity is going to be a matrix. If it just had one component, it's going to be 1. When we had 2 by 2, the identity was here. But see, this is like a trivial case, just a 1 by 1 matrix. So what would give this? Well, actually, if you have U of theta equal to e to the I theta, and put that in there, so you had, say, your matrix had e to the I theta, then everything works. All right, let's go ahead and demonstrate. Closure means that if you take U alpha, U beta, that has to be in the group. And here I'm just going to multiply these things, because if you had the matrices with just one component in there, you just as well write this as the one component. So that means this would be e to the I alpha, e to the I beta, and multiplying these together, you get e to the I alpha plus beta. So that would be a new angle. And since the group has all the angles like we're in, we're good. And then we do association. This is nice that we get to review groups. You know, if you want, you can formally put the U inside a matrix like this if you want, and have the other one in like that. But you see, you're going to basically be multiplying these three things together, and you can multiply in any order. You can multiply these two first, and then you'll have e to the I alpha plus beta, and then this is e to the I gamma. And then when you multiply this one in, you're going to sum up. But if you did the other two first, you would have this. But when you put them all together, you're going to get alpha plus beta plus gamma. And this is going to be alpha plus beta plus gamma, so it doesn't matter. So since numbers, have association, this is going to be association. Is there an identity? Well, I claim the identity would be U with the angle 0, because then you would have e to the 0 as 1, and that wouldn't change the element. And then for inverse, the inverse would be to take e to the minus I theta. And that's consistent with the dagger. See, if you take the dagger, that's going to be the star. You're going to take the star, and that is going to have to be the inverse based on the definition of unitary, and it is. So it all checks out. Here, do they commute? Well, actually they do, because if you take here e to the I alpha and e to the I beta, that would be equal to e to the I beta, e to the I alpha. So this would be an abelian group, since that works. That's good. So you may wonder why we're doing all this, matrices and group theory. Well, this helps us understand the spin of the electron. And this class, we're going to really show you where the spin of the electron comes from. That's going to be with the Dirac equation. Okay, so 2, we're going to look at SU1. Now, SU1 means that you have to be special and unitary. The U stands for unitary, which we just did, but now the special means that also the determinant of U has to be 1. But remember, in general, we just did the case where if we had, say, some unitary, the matrix, we had some little u sitting inside there 1 by 1. And if the determinant of U has to be 1, that means U has to be 1. It's only 1 by 1. So when you do the determinant, remember how we did here? We did A times D minus C times B, but there's only just one component, it's 1. So that means for the group SU1, you just have one element. That's it. That's it. It's one element. If you multiply it by itself, you get the same thing back, so it closes. Association is going to work. It's going to have an inverse itself. Just have a group with one matrix. It's one matrix in the group. So let's go on here with special unitary groups 2 by 2. So now we're going to start with the 2 by 2. A, B, C, D. And the inverse will exist provided that our determinant here is not going to be 0, because we don't want to divide it by 0. And remember here we swap the D and the A, and we put minus signs in front of the other components. All right? That's our prescription to find the inverse. Now you might want to say, well, you really didn't prove it for that other case. But if I go ahead and do this, A, B, C, D, and this is D minus B minus C, A, I'll just go ahead and see if it works. So if you look at this is going to be A times D minus B times C, A times D minus B times C. You take that sideways like that. And if you take this sideways on this, you get A times minus B and B times A. That's going to be 0. And then here, C times D plus a minus D times C. That's going to be 0. And then here, this is a negative BC plus AD. But the determinant is AD minus BC, which means I get a 1 up here, and this is a 1 also. So that means I get a 1 up here and a 1 down there. So like this is going to be, it works. So now I have proven how to get the inverse for a 2 by 2. Okay, so we're doing pure mathematics here, which is amazing that this has application with physics. But these are just definitions using group theory and matrices. So now what we would like to do is we would like to put some of the conditions on our general matrix here. So for the case of unitary, for unitary, we need to have, remember the dagger has to be the inverse. That's what unitary means. So that means the inverse, if we take the dagger, now remember when you take the dagger, what we do? We transpose and put stars. So if we transpose, we have the A and D stay where they are, and we swap the B and the C, and then we star everything. Okay. So we have to have matrices that have that condition. So the condition is, remember that the general matrix that we have up here, which we'll just copy down again, just so you have it next to each other here. You have this is the general inverse for the ABCD. Now this has to be the case. So that means A star has to be equal to D, C star equals minus B, B star is minus C. That's, well, we don't really need that one, since if we star this, we would get C back, and if we star that, we would get B star. So it's kind of, we've got them pretty much, it's redundant. We got these. And then the determinant is AD minus BC, and now, remember, the special, if you want the special case, so it's not just unitary, but they're special, the determinant has to be 1. So for unitary, you have to have this condition above, and then for special, you have this. Now, this is really nice that we're studying mathematics here and group theory independent of physics. This is very nice. And then there'll be a big payoff later when you see there's an application, just like when you study calculus as calculus, then you see you can use it in physics. It's amazing. So it's a math class today. Okay, so now what we're going to do is say, well, I would like to write the general matrix as a real component plus I times the imaginary component. Now, when you do it like this imaginary A sub I, this A sub I is real. So when you hit it with the I, then you get your imaginary component. So this is B real plus I times B sub I, where B sub I is defined to be the regular, number, real number that hits that I. Then down in here, we want this star. In other words, C has to be, in fact, if you look at this is the same as C is minus B star, which you can see here. See, minus C is B star, consistent. So that means take this thing, and if you star this thing and put a minus sign, you'll have a minus BR. And if you star that, that's going to be a minus I, but then this minus sign will make it a plus. And this will be a B I. So you're taking the star of this thing. So if you take the star of this thing, you would have BR minus IBI. But then if you put the minus sign in, the minus sign goes to the BR, and this becomes a plus sign. And the last thing here, down in here, this D has to be A star. So that means take the A sub R and put a minus sign in front of the I. So we have that. Now for the special case, the determinant has to be 1. So if we were to do that, we would have the AR plus AI, this multiplication minus the other one. So this multiplication minus this multiplication, which is BR plus IBI, writing the top one first, and putting the here, you would have a minus BR plus IBI. Okay, now if you look at that first one, that determinant here, this first one is going to be AR squared plus AI squared. Now the second one is actually going to be the same thing with the b's, because if you put that minus sign in here, this is a plus and that's a minus. So you have the sum and you have the difference. So that's going to be a br squared plus a bi squared. And that has to be 1. So you want to find out what these matrices are. And the matrices are going to have these conditions, and we're going to look at this general form and think of the general form the way we would think of like a vector, where you can write a vector as an a sub x I hat plus an a sub y j hat plus an a sub z k hat. And what we're going to do, like for the I hat, j hat, k hat, that kind of thing, we're going to use this kind of a matrix, and then we'll have this kind of a matrix. We'll just put we're going to have 4 of these with a 1, and we're going to ones in place. In other words, and this is an analogy. So the analogy is, if we have the matrix A, B, C, D, we're going to write this as an A, 1, 0, 0, 0, and then we'll have a B, 0, 1, 0, 0, and then we'll have a C, 0, 0, 1, 0, and then we'll have a D, 0, 0, 0, 1, and that works. And these are like basis vectors, like the basics, like your basis, like your unit vectors. It's a similar idea, all right? But now we're going to take another good look at our general A, which we're going to copy down again, what we have. We have AR plus I, AI, BR plus I, BI minus BR. We're basically copying this over again. But there seems to be a natural way to find 4 basis, matrices here. It's suggested, watch this trick. It's suggested that if we take the AR, that we would hit that with 1, 0, 0, 1, because see, that would get you these 2. That would get you this one, and it would get you that one. Isn't that nice? Then, if we focus our attention on I, AI, up here, there's 1, and there's none over here. There's none down there. And over here, there's a minus 1. So that's like suggested to have a different set of 4 rather than the 1, 0, 0, 0, and 0, 1, 0, 0. We're going to have like a different combination. Then, if we go plus BR over here, it's suggested there's no B's up in there. There are no B's down in there, but there is a BR up in there, and there's 1 down here, and that one is a minus sign, like that. And that takes care of the BRs. And then the last thing is the IBI. There's none up here. There's none down there. And up in here, there's an IBI, so that would be a 1. And then down here, there's an IBI, that would be a 1. Okay? So I notice I have an identity here, the identity matrix, but then I have these 3 other interesting ones. I'm going to call this one sigma x. I'm going to call this one up here sigma z. But now I have a situation where I don't have an I out here. I kind of would like to have an I out there, because I have an I here and I have an I there. So if I were to look at this one, and put an I on the outside so that, I have an I with something, then I would need to have here a minus I to get the 1. And then here I would need a plus I, so an I squared to get the minus 1. I would get this. And I'm going to call this one sigma y. Now, I would have loved to have seen this when I was a student, because I have just shown you a natural way to get the Pauli matrices. These matrices are named after Pauli. There he is, Wolfgang Pauli. And the Pauli matrices, go ahead and write them down again. This one here, 0, 1, 1 like that, 0. And for the y1, 0 minus I, and 0. And for the z1, 1, 0, 0, negative 1. And the other basis vector, you could say, or basis matrix, is the identity, where we have the identity as the fourth one, which was the natural decomposition that occurred when we studied this carefully. This broke out. They usually just throw you those Pauli matrices, just throw them at you, and they're beautiful matrices, and here I'm showing you a natural way to arrive at them, which in theoretical physics is the goal, to show where everything comes from. Now check this out. Check this out. If you take the x and the y, like this, you get 0, 0 plus I, 0, I plus 0, 1 times 0, 1 times 0 is a 0, and then this is a minus I. So this is I times the z1. Now, if you go and flip the order so that you have the y1 first and say the x1 second, then you get 0, 0 plus, this one's negative I, and then 0, 0 plus negative I1 is going to be negative I, 0, 1, and this is 0, 0, I, 0, 0, 1, 0, and then here this is going to be I1 plus 0. So this one here is going to be, if you take the minus I out, you get this. Now, they're not the same, all right? So that means we do not have commutation. In fact, if you have, this is called a commutator, where this by definition means you do the first two in the same regular order and then you minus, flipping it. Well, if I do that, then I get a minus sign there. I would get 2I times the z component. And you find this is going to be true in a cyclic fashion, that if you took here, for example, y with z, x, y, z, this will be 2I sigma x, x, y, z. It's good for you to try these and work some of these out. But now watch what happens if you were to take the anti-commutator. Now the anti-commutator says you're going to take the multiplication, but then when you switch them, you add them. Well, if you add these, you get 0. And you'll find that's true for, let's say, you'll find that they're true for when they're different. If they're the same, like this, then when you have 2 of these, you'll find that this is going to be 0, 0 plus 1, 1, 0, 1, that's 0. You'll find that it's 2 times the identity. But with matrices, by the way, you can use that bracket or you can go ahead and do this. I mean, either way works. So what we're saying here is that if you take, for example, the anti-commutator of two of these, say a J and a K, where the J and K are 1, 2, or 3, if they're the same, you'll get the identity, and if they're different, you're going to get 0. So you say 2 delta JK, where this is going to be 1 if J equals K, and 0 if J doesn't equal K. And then when you do the other one, the commutator, where you have, say, a J and a K, you're going to find that you're going to get 2 of them. If they're in a cyclic form like X, Y, Z, you'll get 2I, and there's this little symbol, JKL, where the way this symbol works is if you have JKL equal to 1, 2, 3, you then get a 1. And if it's cyclic, you still get 1. But if you swap 2 of these together and have a 2, 1, then you get a -1. So if you were to swap these, then you would have, say, the minus case. So this is a very, very shorthand notation to like express the commutator and anti-commutator. So commutator and anti-commutator. And it's good for you to check these out, to do a few of these. It's kind of nice to do that. By the way, these are named after these symbols. The Kronecker delta symbol named after here Leopold Kronecker. And the Levi-Civita or Levi-Civita symbol named here after, say, these individuals. That's called the permutation symbol. So if you hadn't seen this before, just here, I wrote them all out for you. Not sure if you maybe saw that in a math class before. So if you have I, J, K in order, 1, 2, 3, 1, 2, 3, 1, 2, 3, and that's called cyclic, you get a 1. If you swap 2 of these, like see in this case, 2 and 3 got swapped, that's going to be a negative. But then if you cycle these, where you have 1, 3, 2, 2, 1, 3, then they're all going to be -1s. And then if any 2 are the same, you get 0. So that's a nice symbol. This one's easier. If the I equals J, you get 1. If it doesn't, you get 0. And that's how you can write these matrices. I do recommend you working a few of those out. Okay, let's go on here to 4. SO2. I'd like to introduce this one because this is our friend, the rotation matrix that we already have studied. In other words, when you look at this and have the cosine of theta, the sine of theta, minus the sine of theta and the cosine of theta. And this is special orthogonal matrices. That's what that stands for. We could think of them also as, the matrix. The matrix here, A11, A12, A21, A22, same thing. And what does orthogonal mean? So let's look at what that means. If you were to think of these as like 2 vectors, like here's a vector and there's a vector, then if you did like the dot product, you would get 0. In other words, here, if you had, say, a vector A, which was cosine of theta, say like an I hat, plus a sine of theta, J hat, and then the B vector was minus the sine I had, just making vectors out of these, cosine of theta j hat. If you do a dot b, you would get a negative product and here positive, and you would get 0. So that's where the term orthogonal comes from for these matrices, how they make the group nomenclature. Notice that the transpose is the inverse. If you transpose this, right, where let's say you go with the AT for transpose, then you would have the minus sign up in here by just swapping those. But you could then write this as the cosine C of a negative theta, since the cosines are even. And you could say this is here going to be the sine of a negative theta. This is minus the sine of a negative theta, and this is the cosine of a negative theta. So in other words, the matrix is doing the inverse. It's like taking you back the other way. And if you would like, you can just go ahead and prove it another way. You could just say, if you take these two like this and have the cosine and the sine minus the sine, cosine, and then take the one where you have done the transpose, where you transpose the off diagonals like this, then if you do the product, you have cosine times cosine plus sine times sine, that's a 1. Cosine squared plus sine squared. Cosine hit with the negative, and then sine hit the cosine with the positive, it's 0. Here, a negative with the cosine and plus the product's gonna give you 0. And then here, last one is sine squared plus cosine squared give you 1. So that's another way of proving it. And that's the special, since the determinant here is 1. In other words, if you take this minus that, you get cosine squared plus sine squared. So that's where the special comes in. And here you have the orthogonal situation, as I explained, so special or orthogonal matrices. And these are, these work in any order, so this also, in terms of applying the binary operation, this is an abelian group. Okay, now we go on here to J3, eigenvalues. And here's where we apply some physics. The spin of the electron can be up or it can be down. This is where we see some application. And we have the Pauli matrices, which we can write down here. And here, if we take, say, this Z1 and have that operate on 1, 0, you have then 1, 0, 0, negative 1, and the 1, 0. And you would take these sideways, hit that, you get 1 times 1 plus 0 times 0. And then if you go 0 times 1 plus minus 1 times 0, you get this. You get the same thing back, and the coefficient in front, see, is a 1. So we call this an eigenvector for this operator. That's the eigenvector for the sigma z. And this is called the eigenvalue. Let's take the other case where it's 0, 1. Then you would have 1, 0, 0, negative 1, 0, 1. Turn this sideways, you'd have 1 times 0 plus 0 times 1. And turn this sideways, 0 times 0, negative 1 times 1 is negative 1. So this would get you the same thing back that you started with. So that's an eigenvector also. And this here would be the eigenvalue. It's a negative 1 in this case. Let's try to find the eigenvectors for this sigma x matrix, which is this one. So then sigma x operating on some column vector would have to be some lambda and get back the same thing like this. Well, if we put in for what this is, 0, 1, 1, 0, like this, and then C1, C2, and that's equal to the lambda C1, C2. The trick is to subtract the right-hand side, from both sides, and then if you do that, what you'll get is, you can think of this, here's a nice little trick. This is the identity element working on C1 and C2. So now if you subtract, you can think of this as here a minus lambda, 1, 1, minus lambda with the C1, C2 equal to 0. So think of this as being on the far right, and think of subtracting 0, 1, 1, 0 with, or subtracting these two, because all of this is going to be operating on the C1, C2 to equal to 0. And then if you do that, you'll see that the lambda is a minus sign up in that upper left-hand corner, because see, this one is adding plus minus lambda, 0, 0, minus lambda. So you're putting the minus lambda, and the 1 is there, and then the 1 is there minus lambda. So you then wind up with this equation here. And you might recall that when you have two equations with two unknowns, that you have Cramer's rule that you can use. And I went ahead and review for you in the book Cramer's rule, that if you have two equations with two unknowns, ax plus by equals z and cx plus dy equals f, then when you solve for the two unknowns, you get the solutions formally as determinants. If you don't remember this from high school, it's not a bad idea for you to work out from the book what I have here. I have all the steps here, just kind of work it out pretty much on your own. Fill in some steps. Yeah, you may have to do a little bit of work here to solve two equations with two unknowns to get this, and convince yourself that this works. Now the problem is, if E and F are 0, because that's what we have in our case, we have zeros over here, then you're going to find that, this is going to be 0, and this is going to be 0. And for you to have a solution, you have to have an indeterminate form. You'll have to have, down in here, you'll have to have a 0 and a 0. So in other words, the determinant of this matrix will have to be 0 when you have E and F to be 0. And that's what we have. If you look over here, we have over here a big 0. So this is saying 0 and 0. And see, this is like our E and this is our F in this equation over here. So to get a solution out of this thing, we're going to have the determinant of this determinant here to be 0. So then you would have an indeterminate form, and you would have a solution. So that means when you get this set up, the next step is to take the determinant of minus lambda 1, 1, minus lambda, set that to be 0, and that means here you multiply these together, lambda squared minus those 1 equals 0, and lambda squared equals 1, lambda equals plus or minus 1. See, there's your solution. Isn't that cool? Very, very interesting mathematics. So go back and do study. Good law here, Cramer's formula from high school algebra. That's where they usually would introduce that. And it basically solves two equations with two unknowns, ax plus by equals z, cx plus dy equals f. They're your two equations. The unknowns are x and y. And when you solve it, you can write the solution as a ratio of determinants. But then if this happens to be zeros over here, then you need to have the determinant below to be zero, so you have an indeterminate form to get yourself a solution. Okay, so now what we do is we want to find the eigenvectors. So to find the eigenvectors, we have, here's our matrix, and if we multiply C1, C2, we're going to have the eigenvalue here, and the first one for 1, okay, we have the first case here is going to be 1. If you multiply this out, you get the C2 pops upstairs, 0 times C1 plus 1 times C2. And then when you turn this sideways, you get the C1 downstairs. And this has to equal, for the first case, plus 1, C1, C2. And that means that C2 should be C1 and C1 should be C2. So in other words, the eigenvector, which I'll call U, will be equal to 1 and 1. And what we do is put a normalization here, the square root of 2, because what we like to do is we would like to have C1 squared plus C2 squared to be 1, or in general, because you can have complex things, you want this. And that's very important for physics, that if there's an electron, it would spin up and spin down, a probability is 1/2 the time it's spin up, 1/2 the time spin down. So you want to do that. And the last one would be to take this same equation and put a minus sign in, where the eigenvalue is minus. So if you do that, then you could just take it from here. You would have C2 over C1 would be equal to a minus C1, C2. So that means C2 is opposite C1, C1's opposite C2. So an easy way to get that is to have a 1 and a minus 1. And we go ahead and put the normalization in. So that's the eigenvector. So here C1 would be 1 over square root of 2, and C2 is negative 1 over square root of 2. And that satisfies this condition that C2 is negative C1, C1 is negative C2, and we have normalization. Okay, that's it.